So in section 6.8, we turn to science in terms of exponential growth and decay. So instead of our money growing, we're going to have populations growing. And populations can mean any kind of animal growing. There are two formulas to know here. We have our growth formula, which is going to look very familiar. Your book uses A of t is equal to A naught e to the kt. That should remind you of the PERT formula in the previous section. All we're doing is changing some of the letters. E is a constant, that's not going to change. Notice time is also there. A naught is the population at time 0, and K is our growth rate. And we know that when you have a positive exponent on an exponential function, that it's going to look like this. So this is a growth picture. And again, K is going to be our growth rate. And A naught is the population at time 0. So A naught is the population. It's how many people, animals, critters you have in the beginning. And then we also have a decay formula, and this is used mainly when something is decaying. And so we talk about half-lives of like radioactive uranium, potassium, half-lives of carbon-14 to use carbon dating, those kinds of things. And that formula is almost identical. The difference is that in order for it to decrease over time, we know we need a negative exponent. So a decay function would look like this. And that's what the negative exponent is doing. It's doing a reflection across that y-axis for us. K is still the decay rate. T is our time, and A naught is again the population, or how much of the substance you have when you begin. One of the things to note is that you basically can just remember the PERT formula and just use it with the beginning population instead of the beginning amount of money. So basically the same thing. So to start off with example 1, we'll go kind of easy. We'll give you everything and make sure you understand the formula itself. So for example 1, we're going to talk about a number of bacteria. It says the number of bacteria present in a culture at time t in hours. Wait, I'm going to stop. Let's make sure that makes sense. So when we did money, all the time had to be in terms of years. Now your time can be in terms of any unit of time. It could be minutes, it could be hours, it could be days, it could be weeks, it could be years. So notice all of a sudden that time does not have to be in years. This particular one has time in hours. Obeys the law of uninhibited growth. So uninhibited growth is another word for exponential growth. Depending on the textbook you're using, they will either use uninhibited growth or exponential growth. So, and then they give us an actual formula. So it says N of t, N standing for number, is equal to 1,000 e to the 0.01 times t. And there's our formula. So the very first question they're going to ask us is to determine the number of bacteria when t is equal to 0. Okay, well, we can actually do this without the calculator. So N of 0 would be 1,000 e to the 0.01 times 0. Well, 0.01 times 0 is 0. E to the 0 power is 1. So this whole thing is basically 1. So this 1,000 is your beginning population, which we said just a few minutes ago, because that's sitting where A naught would be. So that constant or coefficient out in front is always going to be your beginning population. It's how many you're starting off with. Part B is asking for the growth rate. So the growth rate is sitting up here as this decimal. So for us, our K, our growth rate is 0.01, which will be 1%. So it's a 1% growth rate. Then finally it asks part C, what's the population after 4 hours? So now we're going to find N of 4. So how many bacteria has our culture grown to in terms of 4 hours? So we're going to have 1,000 e to 0.01 times 4. And then straight number crunching through on your calculator. So number crunch that through. You're going to end up with 1040.8. And this is in terms of bacteria. Now, personally, I don't like a part of a bacteria, so I would round this to 1041. Please make sure you read the rounding directions on the MyLab Math carefully and round as indicated. So we end up with, after just 4 hours, 1,041. And that's because it's a pretty tiny growth rate. 0.1% growth rate, not very large. In part D of the problem, they want to know when will the population reach 1700. So N is going to be 1700. They're asking us to find the time. So we're going to set 1700 equal to 1000 e to the 0.01 t. And then we can go ahead and solve that. So to solve that, we've done this several times now. We're going to divide out that 1000. That's going to give me 1.7 equals e to the 0.01 t. Then our next step, in order to bring this t down out of the exponent position, is to take the log of both sides. Specifically, we'll use the natural log. So the natural log of 1.7 is going to be equal to the natural log of e to the 0.01 t. The reason we do that is on the right side, we'll move the exponent out in front, and the natural log of e is 1, and that's going to disappear. So what we really have is just the natural log of 1.7 equals 0.01 t. And then we'll divide out the formula. So t is equal to the natural log of 1.7 divided by 0.01, and that's going to come out to be 53.1, and this is in hours. So after 53 hours, we've gone from 1,000 to 1,700. So, you know, it's a little left, what, a little more than 2 days. Okay, they're starting to grow now. And then finally, part E is asking when the population will double. So how long until it doubles? And after doing all that work in the previous section, we know that when they're doubling, if we started with 1,000, then N would be 2,000. That's the double. So same process we just did. 2,000 is equal to 1,000 e to the 0.01 t. And now we're going to go solve it for t. Same process exactly. We're going to divide out the 1,000. That's going to give me 2 is equal to e to the 0.01 t. Then we'll come in and take the natural log. And the reason to do that is to bring the exponent down. So natural log of 2 is equal to 0.01 t, natural log of e. Notice that I went ahead and moved it out in front. Natural log of e is 1. That's going to disappear. So t is basically the natural log of 2. That's the doubling. 2 is the doubling over 0.01. If they were asking for me to triple this, then literally at this point I have the natural log of 3 over 0.01. So in some ways you can start to take some shortcuts and it's okay. And when you do this, you end up with t equal to 69.3 hours, which makes sense. We know that after 53 hours, we were at 1,700. So to get to 2,000, it's going to take just a little bit longer, right? So, and there it is. So that's your first one. But they gave us the formula. So they kind of walked us through that one. How you do this when they don't give you any formula to start or a function to start. So example 2 talks about the population of a city. The population of a Midwestern city follows the exponential law, the law of uninhibited growth. If the population increased from in 2003, there were 800,000. And then 2 years later, which is just huge, there was 900,000. Now what they're asking us is 2007 with the population. So that's all they're giving us. They did tell me that it's exponential growth. So because it's exponential growth, I know to use A of t. So sometimes I forget to write my t. A of t is equal to A naught e to the kt. And that's only because it tells me it's exponential growth. I know to use that as my template. So our very first step we do is we have to find k because we don't know the growth rate. So step 1, we need to find k. And to do that, I'm going to plug in the initial set of circumstances. We know the beginning population. We know it's 800,000. So that would be e to the kt is equal to A of t. But we also know that 2 years later, the population's grown to 900,000. So we're going to set 900,000 equal to 800,000 e to the 2 times k. So we're replacing t with the 2 years, and now we can go find k. So the very first thing we're going to do is divide out the 800,000. That's going to give me 9 over 8. Now, if that divides out to be a nice decimal, go ahead and divide it at this point. But if it's not, keep it as a fraction because you don't want to use any rounding errors with those other decimal places. So I'm going to keep it as 9/8 is equal to e to the 2k. And again, you'll do this, I don't know how many times in this assignment. We're going to take the natural log of both sides. So we have the natural log of the 2k, the natural log of e. The natural log of e is 1. I'll write it in a couple more times, but after that, I'm going to quit writing it in because we know it's going to disappear every time. So K is going to be the natural log of 9/8 all over 2. And make sure you use parentheses around that 9/8. Close the parentheses before you hit divided by 2. And if you do that, you're going to get K is equal to a decimal, which we expect, 0.05889. I'm going to use 4 numbers, not zeros, not counting that 0, but 4 numbers in my values for K, and then I'll get the answers that are in the textbook. So when you're doing the online homework, that's what I would recommend also. So we have a value for K. So we now have a function. We know that A of T is equal to the initial population of 800,000. E is 0.05889 times T. So now if you give me either a population, I can find the time, or if you give me a time, I can find the population. Specifically, they want to know in 2007. So in 2007, we know that T is equal to 4 years, and that's 4 years after 2003. So 4 years into the future of this population. So we're going to find A of 4. So that would be the 800,000. E to the 0.05889 times 4. Straight plug and check on the calculator, and you end up with something fairly large. You end up with 1,012,000. And if I round to whole people, 494. And again, if you're getting a number slightly different, it's because you use different decimal places on that 0.05889. Okay, and those are both examples of exponential growth. The population is getting bigger.